Hello, everyone. My name is Tianqi. I'm a fourth-year PhD student, and this presentation summarized the most recent work. We developed such an instance-level node profiling for graph structure data. Well, understanding from the previous two talks. No, not this. Wait. Okay. From the previous two talks, I understand that my topics are a little bit different from in your research group. So, as a motivation for studying such a topic, let me describe a scene that feels very familiar. So, it's a common day. You sit in the lab and you receive such a machine learning task for which you have already successfully did literature review. You collected the two most competitive baselines, A and B. And then our novel idea magically achieves consistent 4% of improvement over all the baseline. And after doing all this experiment, now what should I do? It seems like the numbers are looking great. Now it's time to write something down. In the experiment analysis, normally we would write something like compared to baseline A to B, B achieves 2% more of improvement. And based on top of that, our model achieves up to X% of improvement. Well, all of this experiment analysis based on such evaluation metrics such as accuracy, F1 score, or whatever metrics there is, works for your task. And then the next thing to do is to summarize the data properties and put it in a table. And then seems like the paper has already written itself. Have we done everything? Is the paper ready? The answer that remains unanswered here is why. Why did baseline A compared to baseline B performs worse? Why did our model perform better? And the solution to answer such questions is to draw a connection between the model-centric analysis to the data-centric analysis, where from the data-centric analysis, basically we answer the question about how did the baseline perform, how did our method perform, and from a data-centric analysis, we answer the question of how do data sets look like and where do they come from, which field are they, co-authorship graphs or like social networks, and et cetera, et cetera. So what we do here is by combining the model behavior analysis with the data properties, we manage to answer the questions on this specifically kind of data. Model A from this specific category would excel or fail because it utilized such properties from the data. And then we move the analysis from a global view, which means on this data set, model A performed better than model B, to a instance level view, where we ultimately find the answer to the why question. So to collect evidence that such behavior difference do exist, we did a small experiment here for a given data set and a given machine learning models. We collect all the checkpoints during the training process, and then we classify nodes as easy if the model makes consistent high confidence prediction for the true label of the nodes. And the hard nodes are where the models make consistent wrong predictions. And all the other unsure fluctuated decision belongs to the category of ambiguous nodes. So here we see during the training process, by observing the checkpoints, the model learns quickly the pattern from the easy nodes and learn to predict their true labels with very high probability. And the average probability predicted for the true label for the ambiguous nodes remains around 0.5, which is not much different from the beginning where the model just makes random guess. And what is interesting to observe here is while the model learns to learn the pattern from the easy nodes, it actually sacrifices the probability of the true labels for the hard nodes. And the second scenario is what I described, that saying that our model just magically performed better than all the baselines. It's a very good day. normally after all the hard works, all the experiments, and then our model just performs 0.5% of the improvement. And then now what do we do? Would it still be possible to see the difference in the model behavior instead of, because 0.5% of improvement makes it very hard to argue that our model makes significant improvement over all the collected data set. And then we need more evidence to see that our model performed differently than the baseline A and B. So in this paper, we argue that the reason why this the solution to answer that question is to move from this aggregated metrics such as accuracy, which provide the overall performance of the model of a given data set to instance level. So I do believe that the scenarios described in the previous slides extend to several machine learning tasks. But in our paper, we focused on the node classification task in the transductive setting, where we are given the graph topology, the input features, the descriptions of the nodes, and the incomplete labeling of the nodes. And then the task is to predict the labels of the unlabeled nodes. So the framework is designed in such a manner. First, we have created interpretable scores for the nodes in the graph, which we learned from the previous literature that was very important for the graph neural networks to make a right prediction, such as how different these input features are from other nodes from the same class, or how does the in a direct neighborhood label distribution looks like. And if I run the random walk from the ego node to a certain length, how high is the chance that I run into nodes from other classes? And this model-centric profile is where we measure how consistent and how confident the model was by making the predictions of the nodes. And then by drawing the conclusion together, we managed to analyze it in this way. For example, here in this example illustration, we had a 3D plots where the x and y axis are the model-centric profile, which we see where does the model make high confidence consistent prediction, and the z-axis is the data properties. For example, here is the input feature dissimilarity. And then we see clear clusters in such plots, meaning that the easy nodes and the ambiguous nodes have a certain pattern. For example, here, that the nodes that normally have very similar input features compared to other nodes from the same class are easy for the specific nodes. And the third thing that we did is inductive profiling. So in the current practice of machine learning, we train a model on the training data, and then for the unseen data, we do not really have the true labels. And then you make your, you choose the best checkpoint of your model and make a prediction on the unseen nodes. But we don't have assessment of how reliable such prediction of the model on unseen data is. So here, by using NodePro, we can run the KNN clustering algorithm in the latent space, the representations learned for the unseen nodes. And then by taking the categorization of the nodes around it, we can assign the easy, hard, or ambiguous categorization for the node. And then we know how sure our model was while it's making its prediction. So here is what we found by utilizing NodePro. So for a given task, for example, Cora, and then we collected three graph neural networks, GCN, GAN, and GraphSage. And then we collected such empirical results. Here, the two columns represents two different experiment setup, which does not really matter in this research question. I will explain it later. So we can see that all of the graph neural networks collected perform rather similarly. And then by using NodePro, we categorize the train nodes into easy, ambiguous, and hard. Here, the color scheme is consistent. We always use green to represent the easy nodes, the orange for ambiguous, and the red for hard. So we see that although the overall accuracy are all the same, the differences are within 2%. GraphSage finds significantly more nodes as easy, which means GraphSage finds more nodes where it makes very confident, consistent prediction on. Well, GCN and GET struggles with majority of the training nodes because it signs the characterization of ambiguous. So there was some of the fluctuation during the training process. And then another thing that I found very interesting is this overconfidence of a model. The model makes a prediction, but so here in this 3D plot, we also use the same color scheme. So the X and Y axis are the epistemic and allotoric uncertainty, which we get from the model profiling parts. And the low allotoric uncertainty represents high confidence. So you see here from the 3 data pattern perspective, all the hard nodes and easy nodes are with very low allotoric uncertainty. This means throughout the whole training process, the model is making wrong predictions, but it's like very, very confident about this prediction. It's learning nothing over the hard nodes. So here it raises the question about what is a good model. We want a good model that it makes the right prediction with the high confidence. But by using NodePro, we get to see that sometimes the model is just making wrong predictions, but with very high confidence. And also we managed to use NodePro to find out why do models struggle on some data set. So here is where is the 2 columns are coming from. So the left column, I used the partial train setup where I used the 60% of the data for training, 20% for validation, 20% for test. And then the right column is I used all the data for training and all the data for test, which means the model was exposed to abundant training data, but you still don't see much of the improvement here on the right column. So why do graph neural networks struggle?
Do you mean all the data for test? Just training, right?
Yeah, it's data leakage by purpose. So I used all the data for training, and then it has seen the training data, and then I used the same data for test. And here, what I did was I curated the common hard and easy nodes found by the 3 graph neural networks. And then by plotting the distribution of the easy and hard nodes, we find a clear shift of the distribution. For example, the hard nodes tends to have higher input feature quality scores and higher random work-based scores. This means in this specific data set for graph neural network, the hard nodes are the ones with input features that are very different from the other nodes from the same class, and it lies close to the boundary of the classes. And we also utilize NodePro to do an inductive profiling where we constructed such a knowledge graph with manually injected errors. And then we find out that over 90% of the hard nodes are with injected errors. And 50% of the error nodes are identified as hard. This is also very interesting because this is knowledge graph. By generating the input features, I use the LLMs. So LLMs actually managed to curate a lot of semantic informations to input in the embeddings. So even though I put manually injected errors in it, the graph neural network still managed to predict the right labels for some of the hard nodes. And as a summarization, this NodePro is an interpretable instance level profiling where we try to combine the data and model profiles to uncover hidden patterns beyond this aggregated accuracy or loss metric. And we develop such profiles that can generalize to unseen nodes, which gives us assessment for the reliability of the model prediction. And the next step would be that because where we were designing such data profiles, we can only based on the common assumption that graph neural networks works. If someday new graph neural networks are proposed and then based on more complicated semantics of the data, then NodePro would not be able to curate such properties. And I would also be interested to see how this NodePro is applied to model selection. For example, for some sensitive tasks as this healthcare or like user privacy dependent task, we don't want our model to be so confident while it's making partially wrong prediction. And I would also be interested in to extend the data properties into multi-label graph. So yeah, that's all. Thank you.